way up above our heads in the total silence of space. There's a battle going on. And it's a conflict between our most amazing technology and the, well, raw, unpredictable power of our very own star. So today, we're going to unpack this invisible threat of solar storms. Okay, first, let's set the scene. I want you to imagine the sky above us, but think of it like a city. Low Earth orbit, or LEO, that's the city's bustling downtown core. It is, without a doubt, the most valuable and the most crowded piece of real estate that isn't even on our planet. And it is absolutely packed. LEO is home to these incredible assets like the China space station, the ISS, and literally thousands and thousands of satellites. These machines are the quiet backbone of our modern life, right? They run everything from your phone's GPS to global communications. We rely on them for pretty much everything. But there's a huge vulnerability built right into this city in the sky. What happens when that calm, black backdrop of space suddenly turns hostile? I mean, what happens when our own sun decides to launch an attack? In that question, well, that brings us right to the heart of the matter, a phenomenon known as a geomagnetic storm. So what in the world is one? So forget about weather like rain or wind. A geomagnetic storm is a straight-up cosmic energy blast. It happens when the sun basically burps a massive cloud of energy our way, and that energy then violently slams into Earth's protective magnetic shield. Here's how it all goes down, in 4 basic steps. Okay, first, the sun erupts. It sends this giant cloud of charged particles. We call it a coronal mass ejection, or CME, speeding toward Earth. Second, that energy cloud hits our magnetic field. Third, our upper atmosphere, the thermosphere. It absorbs this enormous blast of energy, and it heats up, like, really fast. And fourth, just like anything that gets hot, it expands. The thermosphere literally puffs up, pushing farther out into space. Now, this is where things get really interesting for our satellites. That expansion dramatically increases the density of the super thin atmosphere up in LEO. So for a satellite, it's like you're flying smoothly one minute, and the next you're trying to fly through invisible syrup. The drag force just skyrockets, slowing the satellite down and starting to pull it right out of orbit. And check this out. This map shows you exactly what that looks like. On the left, you've got normal atmospheric density at about 400 kilometers up. But on the right, during that 2015 storm, all that red shows a massive spike in density. That's the invisible syrup I'm talking about, just taking over the whole area. You know, this isn't just a theory. A recent study decided to run a major stress test, asking a really critical question. What would happen if some of the most powerful storms from the past hit our modern space infrastructure today? And look, we've seen this happen before. This is a real danger. Back in 1979, the Skylab space station literally fell out of the sky, 2 full years ahead of schedule. And why? Because scientists at the time completely underestimated the power of solar activity and the atmospheric drag it creates. So, learning from that mistake, researchers in this new study used some really sophisticated computer models. They took the massive 180-ton China space station as their test subject, and they ran simulations to see what would happen if it got hit by some of history's most powerful solar storms. They chose 3 specific heavy hitters: the 2015 St. Patrick's Day storm, the really intense Halloween storms of 2003, and, of course, the undisputed heavyweight champion of the modern space age, the 1989 storm that famously knocked out power to all of Quebec. Okay, so the simulations were run, the data came in, and the verdict was honestly pretty shocking. Let's take a look at what they found. To really get the scale of this, just remember what that 1989 storm did on the ground. The very same massive surge of energy that overloaded Quebec's power grid was also superheating our upper atmosphere. Now let's see what that same energy does to a space station. 2.6 kilometers. That's the number. If that same 1989 storm hit today, the models predict the China space station would drop out of its orbit by up to 2.6 kilometers. That is a massive, and I mean massive, uncontrolled descent for a space station. And here's what that looks like in the data. See that steep red line? That's the station's altitude. You can see the exact moment the storm hits. The altitude just starts to plummet. The result? A fall of 2.6 kilometers in only 5 days. Its orbital decay rate, that's how fast it's falling, spikes to over 1 kilometer per day. That's a terrifying speed for any crewed mission. And it wasn't just the 1989 storm. The 2003 storm, that would have caused a drop of almost a full kilometer. Even the weaker 2015 storm would have caused an 800-meter drop. The pattern here is crystal clear. The more intense the storm, which we measure in something called nanoteslas, the more dangerous that orbital decay gets. So you see, this simulation isn't just some fascinating what-if scenario. It is an urgent warning, and it points to a critical weakness in how we get ready for these kinds of events. And here's the real kicker. When the researchers compared their models to actual satellite data, they found that even our very best predictions have errors of over 20%. We are consistently underestimating just how much the atmosphere's density spikes, mostly because it's just incredibly difficult to model that complex chain reaction of energy. This chart makes the problem painfully clear. During the 2003 storm, one of the leading models was off by over 42%, another one was off by over 33%. Even the best one was still wrong by almost 28%. In other words, when it matters the most, our predictions are failing us. We are flying partially blind. And all of this is happening at a really critical time. Our current solar cycle, cycle 25, is ramping up to its peak. Longer-term cycles suggest that solar activity in general is on the rise. And at the exact same time, companies are launching thousands of new satellites, making low Earth orbit more crowded than it has ever been. Which really just leaves us with a final, pretty sobering question. The storms we just looked at were powerful for sure, but they're nothing compared to the legendary Carrington event of 1859. With our skies now absolutely filled with the technology that powers our entire world, are we truly prepared for a storm of that magnitude? The data seems to suggest we have a whole lot of work to do.